Welcome to lesson 8 on power system analysis. This lesson is a continuation on transmission line modeling, especially modeling of the long line. Now, if you remember in the previous lesson, that is lesson 7, we talked about distributed parameter model for long transmission lines, that is lines which are longer than 250 kilometers. For these lines, we said that the line voltage V x at a distance x from the receiving end is given by cos hyperbolic gamma x into V r plus Z c sin hyperbolic gamma x into I r, where gamma is called the propagation constant, x is the distance of the point from the receiving end. V r and I r are the voltages and currents at the receiving end. Similarly, the current at a distance x from the receiving end I x is equal to 1 by Z c sin hyperbolic gamma x into V r plus cos hyperbolic gamma x into I r, where Z c is the characteristic impedance of the transmission line, and it is given by square root of Z by y, where Z is the series impedance of the transmission line per unit length and y is the shunt admittance of the transmission line per unit length. As we see, these models, these equations involve hyperbolic functions. Now, since we have been writing all these transmission line equations in terms of ABCD parameters, we can write this equation also in those terms. So, in matrix form, we can use this as V x I x is equal to A x, B x, C x, D x and V r I r. This form where this relationship is in terms of voltage and current at any distance x from the receiving end. Now, here if you see A x is equal to d x and that is equal to cos hyperbolic gamma x in per unit. That is, if you see this relationship, this is your A x and this is your B x, this is C x and this is D x. So, A x is equal to D x is equal to cos hyperbolic gamma x, B x is equal to Z c sin hyperbolic gamma x, B x is equal to Z c sin hyperbolic gamma x, C x is equal to 1 by Z c sin hyperbolic gamma x and d x, as we have already seen, is equal to A x. So, this is the model where A and D are basically dimensionless, B has a dimension of impedance and C has the dimension of Siemens, that is admittance. Now, normally we are interested only in the terminal conditions, that is the sending end voltages and currents and the receiving end voltages and currents, rather than the voltage and current at any intermediate point on the transmission line. Therefore, we can find out the voltage and currents at the sending end in terms of voltage and current at the receiving end by substituting x is equal to L, where L is the total line length. In that case, we will get the equation V s I s is equal to A B C D. Now, we are not writing x because we are now dealing with the terminal conditions only. Therefore, we will have A, B, C and D parameters into V r I r. Here A is equal to D is equal to cos hyperbolic gamma L. Instead of x, we have substituted L. This is a dimensionless quantity, it will be in per unit if voltage and currents are all in per unit. B is equal to Z c sin hyperbolic gamma L, C is equal to 1 by Z c sin hyperbolic gamma L. This B has a dimension of impedance, C has a dimension of admittance. Now, here the term gamma is what we call propagation constant of the line, and gamma in general will be a complex quantity, that is gamma is equal to alpha plus j beta. Its dimension will be per meter. In fact, if you see gamma L, the dimension of gamma L will be dimensionless. So, gamma is equal to alpha plus j beta per meter. Now, if we write e to the power gamma L, this will be equal to e to the power alpha L plus j beta L, and this will be equal to e to the power alpha L into e to the power j beta L. This we can write as e to the power alpha L angle of beta L. Now, here alpha, if you see, is called the attenuation constant of the line, and beta gives the phase angle. So, it is called the phase constant of the line. So, propagation constant has two terms, alpha the attenuation constant and beta the phase constant. Now, if you write cos hyperbolic gamma L, this will be equal to e to the power gamma L plus e to the power minus gamma L by 2. This is equal to half e to the power alpha L angle beta L plus e to the power minus alpha L angle minus beta L. Similarly, sin hyperbolic gamma L is equal to e to the power gamma L minus e to the power minus gamma L divided by 2. This is equal to half into e to the power alpha L angle beta L minus e to the power minus alpha L angle beta L. So, in this way, if we know the alpha and beta, we can calculate the terms sin hyperbolic gamma L and cos hyperbolic gamma L, and therefore, we can calculate V s I s in terms of V r I r. Or we can use the other identity, that is cos hyperbolic alpha L plus j beta L, that is cos hyperbolic gamma L is equal to cos hyperbolic alpha L into cos beta L plus j sin hyperbolic alpha L into sin beta L, or sin hyperbolic gamma L, that is sin hyperbolic alpha L plus j beta L is equal to sin hyperbolic alpha L into cos beta L plus j cos hyperbolic alpha L into sin beta L. So, knowing the z and y, we can calculate the propagation constant gamma and therefore, alpha and beta, and we can also calculate the characteristic impedance Z c. So, knowing these values, we can evaluate the sending end voltage and current in terms of receiving end voltage and current. That is, this relations, using these relationships, we can evaluate the terminal condition of the line. Now, in most of the analysis that we do, especially using computers, most of the analysis that we do, we need a circuit parameter model rather than the ABCD model of the transmission line. As we have said earlier, we had created a pi model or a nominal pi model for a medium length line. Similarly, we can find out, or we can represent a long line in terms of a equivalent pi model. The difference between nominal pi and equivalent pi is only that instead of using Z, which is the series impedance of the line, and Y, the shunt impedance of the line, we have to use here Z dash, which is not equal to Z, but modified value of Z, and Y dash, which is again a modified value of Y. So, some modification into series on series impedance and shunt admittance of the transmission line will have to be used here in the long line model. Now, this is the pi model where we have V s the sending end voltage, I s the sending end current, V r the receiving end voltage, I r the receiving end current, Z dash is the series impedance of the line, and the total shunt admittance y dash is divided into two parts, y dash by 2 at the sending end and y dash by 2 at the receiving end. This is the pi equivalent model for the long line. Now, we need to find out these values of z dash and y dash for making this model complete. Now, we know that for the pi model A is equal to D is equal to 1 plus y dash z dash by 2. This is the same thing that we had done in lesson 7, where we had found the ABCD parameters and the transmission line pi model, nominal pi model parameters. There we had seen A is equal to D is equal to 1 plus y dash z dash by 2 in per unit. This is a dimensionless quantity, and B is equal to z dash, this is ohms, that is impedance units, and C is equal to y dash into 1 plus y dash z dash by 4 Siemens, that is the unit for admittance. Now, using this, here we have z dash is equal to z c sine hyperbolic gamma L, which we can write as Z, which is the series impedance of the line, total series impedance of the line, into F1, or this is equal to Z into sine hyperbolic gamma L by gamma L. Similarly, y dash by 2 will be equal to tan hyperbolic gamma L by 2 divided by Z c. This is equal to y by 2 into F2. This is equal to y by 2 into tan hyperbolic gamma L by 2 divided by gamma L by 2. We will see how we get this relationship. Z dash is equal to Z c sine hyperbolic gamma L. This is equal to square root of Z by y, that is Z c is Z by y, square root of Z by y into sine hyperbolic gamma L. Therefore, Z dash is equal to Z L into square root of Z by y sine hyperbolic gamma L by Z into L. This is equal to Z into L sine hyperbolic gamma L by square root of Z y L. So, this is sine hyperbolic gamma L, Z L into sine hyperbolic gamma L divided by square root of Z y into L. This is equal to Z into F1, where F1 is sine hyperbolic gamma L divided by gamma L in per unit, and 1 plus y dash z dash by 2, that is A, is equal to cos hyperbolic gamma L. Therefore, 1 plus y dash z dash by 2 it is the same equation, or y dash by 2 is equal to cos hyperbolic gamma L minus 1 divided by Z c sine hyperbolic gamma L. This is equal to tan hyperbolic gamma L by 2 divided by Z c. This is equal to tan hyperbolic gamma L by 2 divided by square root of Z by y, that is Z c. Therefore, y dash by 2 is equal to y into L by 2 into tan hyperbolic gamma L by 2, this term. Now, here we have multiplied it by y L by 2 in the numerator, and therefore, we have divided it in the denominator. So, square root of Z by y into y L by 2. Therefore, we will get this equal to y L by 2 into tan hyperbolic gamma L by 2 divided by square root of Z into y into L by 2, which is equal to y by 2 into y L will give me the y, capital Y, that is total shunt admittance of the line. So, this is y by 2 into F2 Siemens, where F2 is equal to tan hyperbolic gamma L by 2 and root y z is nothing but gamma. So, this is gamma L by 2 in per unit. Now, these relationships give us the model for finding out the voltage and current at any point on the line or the terminal conditions of the line, that is sending end voltage and current of the line. These are the accurate ABCD parameters of the transmission line or the accurate parameter for the pi equivalent circuit of the line. Now, most of the time, since we see these relationship that we have seen earlier, these relationships are involving hyperbolic functions. So, doing computation with these is going to be somewhat tedious. Also, many times what we need to do is try to get some approximate idea of what is happening in the transmission line. This is very important, especially when we are designing a transmission line, because we will have to work out large number of options. So, for this purpose, what we do is we try to introduce the concept of a lossless line. That is a line where the series impedance consists of only the inductance part or the reactance of the line, and the resistance is negligible. Similarly, the shunt admittance consists of only the capacitance and the shunt conductance is neglected. One of the advantage of this kind of modeling is also that it gives us a very good idea about some of the important concepts of power flow on the transmission line and other aspects. Now, in case of the lossless line, we have the series impedance per meter length is equal to j omega L, where L is the inductance of the line per meter length, and shunt admittance Y per meter length will be equal to j omega C, where C is the shunt capacitance of the line per meter length. So, this is Y is in terms of Siemens per meter, Z is in terms of ohms per meter. Now, here if we take the characteristic impedance of this line, then it will be Z by Y. Since this line is lossless, we call this characteristic impedance for a lossless line as the surge impedance of a line. So, for this line, the surge impedance ZS is equal to square root of Z by Y, which is equal to square root of j omega L by C, j omega C, which is equal to square root of L by C ohms. Now, if you look at this ZS, you find that this quantity ZS is a pure real number, that is ZS or the surge impedance is pure resistive in nature. It is not a complex number, as we had seen earlier. ZC is a complex number. Similarly, the propagation constant gamma is equal to square root of ZY, which will be equal to square root of j omega L into j omega C. This comes out to be j omega square root of root L C, which we write as j beta, because we find that this term now is purely imaginary, right, and therefore, we have only imaginary term for the propagation constant, or it is in terms of only the phase constant. The attenuation constant is 0, which is natural because there are no losses in this line. So, gamma is equal to j beta per meter, and if you are talking in terms of the whole length, then gamma L will be dimensionless. Here beta is equal to omega into root L C per meter, which is the phase constant. Now, we will try to develop the ABCD parameters for this lossless transmission line. Now, again we had seen earlier A x is equal to d x is equal to cos hyperbolic gamma x. Now, gamma is equal to beta j beta, therefore, this is equal to cos hyperbolic j beta x, which will be equal to e to the power j beta x plus e to the power minus j beta x divided by 2, which is equal to cos beta x in per unit. This is a dimensionless quantity. Now, here we see that A and D are in terms of cos beta x, not hyperbolic functions. Similarly, sin hyperbolic gamma x is equal to sin hyperbolic j beta x, which is equal to e to the power j beta x minus e to the power minus j beta x divided by 2, which again comes out to be equal to j sin beta x. Again, this is a pure trigonometric function, it is not a hyperbolic function. Therefore, B x will be equal to z c sin hyperbolic gamma x. This is equal to j times z c sin beta x. This is equal to j times square root of L by c, z c is root over L by c into sin beta x. Now, again this, if we see, is a purely imaginary quantity or the quantity for reactance. This has a unit of ohm. Similarly, C x will be equal to sin hyperbolic gamma x by z c, that is j sin beta x divided by root L by c. So, this is again an imaginary quantity which is very similar to capacitance. So, with z dash will be equal to j z c sin beta L, which we can write as j x dash. Similarly, y dash by 2 we can write as equal to y by 2 sin hyperbolic gamma L by 2 was there. So, this is j beta L by 2 divided by gamma L by 2 was there earlier. Now, gamma is equal to j beta only. So, it is j beta L by 2. This is equal to y by 2 sin hyperbolic j beta L by 2 divided by j beta L by 2 into cos hyperbolic j beta L by 2, that is sin hyperbolic j beta L by 2, we have put it as sin hyperbolic j beta L by 2 divided by cos hyperbolic j beta L by 2. This is equal to j omega c into L, this is for y, total line capacitance divided by 2. So, y by 2 into j sin beta L by 2, because sin hyperbolic j beta L by 2 we had seen is equal to j sin beta L by 2 divided by j beta L by 2, this term, into cos hyperbolic j beta L by 2 we had seen is equal to cos beta L by 2. So, this terms comes out to be j omega c into L by 2 into tan beta L by 2 divided by beta L by 2. This we can write as j omega c dash L by 2, where c dash is now the modified capacitance of the transmission line, or j omega c dash L is the modified admittance of the line, and that c dash is equal to c times tan beta L by 2 divided by beta L by 2. So, for a lossless line we see that we reduce the relationship from hyperbolic functions for a normal lossy long line to a pure trigonometric function relationship for a lossless line. This reduces our computational burden considerably, and one can do hand calculations with this kind of relationships. Therefore, the pi equivalent circuit for a lossless line will look like this, where V s is equal to V s angle delta, I s is the current flowing, y dash by 2 is the half of the total modified admittance of the line, z dash is the total series impedance of the line, that is the modified series impedance of the line, y dash by 2 the other half of the shunt total shunt modified total shunt admittance of the line is placed at the receiving end, IR is the receiving end current, and VR is equal to VR angle 0 degrees, which is the receiving end voltage. We have chosen the receiving end voltage as a reference voltage, where we have as already seen z dash is equal to j omega L into L is the length of the line into sin beta L divided by beta L, which is a pure imaginary quantity or the reactance J x dash. And similarly, y dash by 2 can be written as j omega c dash L by 2 Siemens, which is purely capacitive. Now, for lossless lines, we can also introduce the concept of wavelength, that is the length of the voltage and current wave on the line as it moves by 360 degrees. That is a total change in phase of voltage and current wave on the transmission line over a 360 degree displacement. Now, if lambda is the wavelength of the line, then lambda will be equal to 2 pi, which is 360 degrees, divided by beta, the phase constant of the line. Therefore, we can write lambda, the wavelength of the line, is equal to 2 pi by omega root L c, beta is omega root L c, which is equal to 1 by f root L c, because omega is twice by f. So, if we write here twice by f, twice by will cancel out, this is 1 by f root L c, which comes out to be about 6000 kilometer for 50 hertz line. Now, this will be approximately 6000 kilometer of the line, because if you see the relationship for L and C, and since we can take r dash, the effective radius in calculating the inductance, to be almost same as that of r, because d is much larger compared to r. Therefore, in that case, if we substitute the relationship for L and C here, then we will find that this comes out to be this much. Similarly, we will get f lambda, that is, if we multiply it here, 1 by root L c, which is the velocity of propagation of voltage and current wave on a lossless line, and this for a lossless line comes out to be same as that of speed of light. So, the velocity of propagation of voltage and current wave on a lossless long transmission line is the same as that of light. This relationship again you can see by simply substituting the relationship for L and C here. This will then come out to be 1 by mu 0 into root over mu 0 into epsilon 0, which comes out to be 3 into 10 to the power 8 meters per second, which will be same as the velocity of the light. Now, for lossless line, we can introduce one more concept which is very important, especially when we are designing the transmission lines or transmission systems. This concept is of surge impedance loading. As we had seen earlier, Vx is equal to Ax into Vr plus Bx into Ir, where Ax is cos beta x in case of lossless line. So, and Vx is equal to Zc sin beta x. Therefore, Vx is equal to cos beta x into Vr plus j Zc sin beta x into Ir, and similarly Ix will be equal to Cx Vr plus dx into Ir. Cx is equal to j sin beta x by Zc, and dx is equal to Ax, which is equal to cos beta x. Therefore, Ix is equal to j sin beta x by Zc into Vr, plus cos beta x into IR. Now, if we terminate this transmission line into an impedance ZC. Now, here this figure is showing you the transmission line or a single phase transmission line. We can consider it also as a single phase to neutral for this transmission line. Now, if we look at this transmission line and terminate it into ZC, that is, if we load this line with an impedance equal to the characteristic impedance or the surge impedance for a lossless line, that is ZC is equal to root L by C, then we get Vx is equal to cos beta x into Vr plus j ZC sin beta x into IR. Now, IR will be equal to, if you look at this circuit, then IR will be equal to Vr, the voltage at this point, divided by ZC, the impedance connected here. So, we replace this IR by Vr by ZC. Therefore, we will get this as cos beta x plus j sin beta x into Vr. This ZC cancel out. So, we get this as equal to e to the power j beta x into Vr volts. Now, here if we take the magnitude of this, then what we get is that Vx is equal to magnitude of Vx is equal to magnitude of Vr, that is the voltage at any point on the line is constant, that is it is equal to the receiving end voltage. So, from sending end to receiving end at all point the voltage is same, that is the magnitude of the voltage is same. This is one great advantage in using the loading on the line which is equal to the surge impedance, and this is a particularly important characteristic of lossless line. That is, if we terminate this line into surge impedance, then the voltage all along the length of the line is going to remain constant. Similarly, we can find out the current at any point x from the receiving end. So, Ix is equal to j sin beta x by Zc into Vr plus cos beta x into Vr by Zc, that is Ir, we are replacing by Vr by Zc. So, this comes out to be cos beta x plus j sin beta x into Vr by Zc, which again is equal to e to the power j beta x into Vr by Zc. Again the magnitude if you take is going to remain constant all along the line. Now, if we talk in terms of the power which is flowing in the line when we terminate this lossless transmission line to through a surge impedance, then we have Sx, the power, the complex power flowing at any point in the line at a distance x from the receiving end is equal to Px plus jQx, where Px is the real part or the real power flowing at a distance x from the receiving end, and Qx is the reactive power which is flowing at a distance x from the receiving end. This is equal to Vx into Ix conjugate. Now, if we do this, then we write for Vx as e to the power j beta x into Vr, and for Ix we write e to the power j beta x into Vr by Zc. We take the conjugate of that. Then if we do this calculation, e to the power j beta x will cancel out and we get Vr square, that is the mod of Vr square in divided by Zc. That is, the real power flow along the line is constant, that is all along the line the real power flow is constant. This is natural because there is no losses which are taking place in the line. So, whatever power is being sent from the sending end, we are receiving the same power at the receiving end, and real power all along the line is constant. And also a very important characteristic of this lossless transmission line being terminated into its characteristic impedance is that reactive power flow is 0. That is, whatever reactive power losses which take place in the line because of the series reactance of the line is being produced by the shunt capacitance of the line. That is, whatever is the reactive power generated by the shunt capacitance of the line, that is being consumed by the series impedance of the line, and therefore, the reactive power flow along the line is 0. So, the surge impedance and surge impedance loading gives us very important characteristic. That is, what we find from this is that if we load the transmission line at its surge impedance, or the surge impedance loading of the line will provide us a constant voltage all along the line. That is, both V s and V r will be same. This is a very great characteristic. That is, the regulation of the transmission line is going to be 0%. There is no voltage drop which takes place. Similarly, we do not have to provide any reactive power support for the reactive power consumed by the series impedance of the line, because reactive power consumed by the series impedance of the line is being provided by the shunt impedance of the line itself, and there is no reactive power flow. So, we can transmit the full capacity of the line in this case. Now, this surge impedance value for different voltage levels of the line is given in this table. These are typical values. These may not be the exact values, but they are approximately the values which we have. So, for a rated 230 kV line to line voltage 3-phase system, ZC is about 380 ohms, and the surge impedance loading in that case is going to be about 140 megawatt. Similarly, same for 345 kV, it is about 285 ohms, and the surge impedance loading is 420 megawatts. For 500 kV, this ZC, that is the characteristic impedance or surge impedance, is equal to 250 ohms, and the surge impedance loading of the line is 1000 megawatt. And if we go to 765 kV, then the value of ZC is again approximately around 257 ohms. This can vary from 250 to 260 ohms, and the surge impedance loading will be about 2280 or 2300 megawatt. Now, what we see from here is, if we go for higher and higher voltages, our surge impedance loading keeps on increasing, and that is why when we need to transmit more and more power, we go for higher and higher voltages, because if you see this relationship, the voltage, that is the power flowing, is proportional to square of the voltage. So, if you are doubling the voltage, you are able to transmit 4 times the power, and so on. Now, I will show you the characteristics of this long lossless transmission line. When we have surge impedance loading, the voltage across the line all along from the sending end to receiving end is going to be same. If the line is unloaded, then the sending end voltage V s or V no load at any distance x, which we can write as at distance L, is equal to cos beta x or cos beta L for sending end voltage into V R and L. Now, in this case we find that the sending end voltage is going to be less than the receiving end voltage, and if we keep the sending end voltage as 1 per unit, then what we find that receiving end voltage is going to be much higher. Similarly, if we do a short circuit of the transmission line at the receiving end, then the receiving end voltage is going to be 0 and the sending end voltage being 1 per unit, we will get the short circuit voltage at any point x is equal to Z c sin beta x into I r short circuit. So, in this case again the voltage that we get will be following this profile, coming down to 0 at the receiving end where the short circuit has occurred, and it will be V s at the sending end. When the line is loaded at some other loading than the series than the surge impedance loading, generally lines which are not very long can be loaded more at loads which are more than the surge impedance loading, that is full load is in general for not very long lines will be larger than the surge impedance loading, and therefore, the voltage for that case is going to be somewhere in between these two conditions, which is the short circuit and the surge impedance loading. There is going to be some voltage drop, and this is what we will find. There is going to be some kind of a voltage regulation for this system. So, again from this we find one thing, that if we load the line to surge impedance, then the voltage remains constant, and that is why when we are designing the transmission line, we try to work on the basis of surge impedance loading, because that is the ideal condition that we would like to have, that is voltage remains constant all along the transmission line. Now, for this lossless line, there is another very important concept that we would like to discuss, and that is steady state stability limit for a transmission line. Now, if you look at the pi equivalent circuit, then we can calculate this I r as I r will be equal to V s minus V r divided by this Z, which will be the current flowing in this minus the current flowing here, which will be V r into y dash by 2. So, if we look at that, then we have I r is equal to V s minus V r by Z dash minus y dash by 2 into V r. Now, substituting the value of V s and V r, V s we said is the sending end voltage with a magnitude V s and angle delta, and V r is the magnitude of V r at an angle 0 degree, because that is chosen as reference. So, and Z dash in this case is only J x dash, because we are considering a lossless line. So, V s minus V r by Z dash can be written as V s E j delta minus V r divided by J x dash, and y dash by 2 can be written as j omega C dash L by 2 into V r. So, into V r. Now, the receiving end power, as we had talked earlier, will be given by this S r is equal to V r into I r conjugate. So, VR into IR conjugate is this term. So, we take the conjugate of that. So, Vs E j delta minus VR by Jx dash conjugate, and the conjugate of this will be negative of this. So, plus j omega c dash L by 2 into VR square, because with this VR gets multiplied on this side also. So, this is equal to VR into Vs E to the power minus j delta minus VR by j minus Jx dash, because we have taken the conjugate. So, this minus of angle comes, and minus Jx dash for that shifting of the angle will come. So, this minus Jx dash plus j omega c L divided by 2 into VR square. Now, if we expand this, then we will get this as j V r into Vs cos delta plus VR into Vs sin delta minus j VR square by x dash plus j omega c L by 2 into VR square. I am sorry, there is a slight mistake here. This should be c dash and this should be c dash. Now, if we look at the real power only, that is, we take the real part of this, then P is equal to Ps is equal to Pr, which is real part of the complex power Sr, then this will be equal to Vs Vr sin delta by x dash. All other terms are having j, that is, they are having imaginary, they are imaginary components, that is, they are terms for the reactive power. So, P, the real power at the sending end, is equal to the real power at the receiving end, and is given by Vs into Vr by x dash into sin delta. This will be watts or megawatts, depending on whether we are using volts or kilovolts. Therefore, P max is equal to Vs Vr by x dash, that is the maximum power that can be transmitted over this transmission line will be equal to Vs Vr by x dash, because this term comes, this will be maximum when delta is 90 degree, that is sin delta is equal to 1. The relationship is plotted here, and it shows how with change in angle delta the real power varies. Now, this is a very, very important relationship. This tells us one very important thing, that the maximum power transmitted over the transmission line depends on the square of the voltage, because normally Vs and Vr will be very close to 1 per unit. So, we will be talking in terms of the square of the voltage only, the rated voltage of the transmission line. So, P max is proportional to the square of the voltage. So, when we double the voltage, system voltage, we are able to transmit 4 times the power. Also, the maximum power which can be transmitted over the line is inversely proportional to the reactance of the line. Now, this is again very important, and we had seen earlier that when we use bundle conductors, then the inductance of the line gets reduced, because the effective radius of the line gets increased considerably, and that reduces this reactance, and therefore, use of bundle conductor will allow you to transmit more power on the transmission line. There is another very important aspect, is that suppose we have a synchronous machine which is connected to the system by means of a transmission line. Now, if we now keep on, if this line, if this synchronous machine is supplying certain amount of power to this system, let us say it is working at this point somewhere. So, the delta angle for this will be there, the power which is being transmitted, suppose here the power which is being transmitted here and the angle, power angle or the voltage angle at the machine is delta 0. Now, if we slowly start increasing the input to the machine, what will happen is the machine output is remaining same, the input has been increased. So, it will experience some acceleration. Since it is synchronized, it cannot accelerate as such, or speed will not change much, but what will happen is the delta angle will start increasing. If we keep doing this, what will happen is delta angle will keep increasing, and as delta angle increases, the electrical power output also increases. So, the mechanical power and electrical power are becoming equal and the machine will be operating in stable region. Suppose we keep doing it very slowly, we keep on moving on this. When we reach this point, when delta is equal to 90 degrees, if we now increase the mechanical input to the synchronous machine, what is going to happen is delta angle will increase, but electrical power output is going to get reduced, which means that there is going to be some accelerating power available. Mechanical input is more, electrical output is less. So, delta angle will keep increasing. As delta angle increases, the accelerating power also increases, which will further increase this delta angle, and machine will become unstable. That is what we see is, if we gradually increase the input to the machine will adjust to that and will increase its electrical power output till delta is equal to 90 degrees. Beyond that, it will become unstable, because the mechanical input increase is not going to be accompanied by similar amount of increase in electrical output, and that is why this P max at delta is equal to 90 degree, which is given by Vs by Vr, Vs into Vr by x dash, is also called as steady state stability limit. Okay, now we can write this P, or the real power, for a lossy line, for a lossless line. P is equal to Vs Vr into sin delta by Zc sin beta L, which is equal to Vs Vr by Zc into sin delta by sin twice by L by lambda, which, that is, we are trying to write the real power in terms of surge impedance loading. So, P is equal to Vs by V rated, we want to put everything in terms of per unit system. Therefore, Vs by V rated into Vr by V rated into V square rated by Zc, that is, this V rated we will get cancelled here. So, V square rated by Zc into sin delta divided by sin twice by L by lambda which is equal to Vs per unit into Vr per unit into, this term is surge impedance loading. So, into SIL into sin delta by sin twice by L by lambda in terms of watts or megawatts, or P max is equal to Vs per unit into Vr per unit into surge impedance loading divided by sin twice pi L by lambda, where lambda is the wavelength of the line and L is the length of the line. That is, we can see that the transmission line value of P max is going to depend on V s, V r, and it is going to, that is, if you increase V s and V r, then the maximum power transfer will increase, and if you increase L, your maximum power which can be transmitted will reduce. And if we plot this curve, we will get this curve like this. This is the theoretical one, whereas the practical one will be much lower, because we normally work at an angle of delta around 30-35 degrees only, not beyond that, normally between 20 to 30 degrees. And here we see that for short lines, that is lines up to 80 kilometers or so, it is the thermal limit which is the limiting factor for the transmission line loadability, and this can be as high as 3 times SIL. But as we go beyond this 80 kilometer length, then the line loadability keeps on increasing with the practical line characteristics with delta around 30 degrees. We will get this kind of a characteristics, which shows that beyond 500 kilometers we have to load the line at a limit which is lower than surge impedance loading. So, we see that if the line length increases, our power transfer capability also reduces. This is the typical surge impedance loading at different voltages, and this is the thermal rating of the line. So, we see that for the lines, the thermal rating for in the most of the cases is much higher than the surge impedance loading. The same concept we can derive for the lossy lines, where instead of using the lossless line, that is gamma being equal to beta, we will use the gamma as a complex number. Then we can write this A is equal to cos hyperbolic gamma L is equal to A angle theta A, B is equal to Z dash is equal to Z dash theta Z. Then we can write IR in the same way as Vs minus A VR divided by B, and substituting these values we will get SR, that is equal to VR IR conjugate, which is equal to VR into this IR conjugate. This term, this will come out to be VR Vs Z dash e to the power j theta Z minus delta minus A VR square by Z dash e to the power j theta Z minus theta A. And PR, which is the real part of this complex power at the receiving end, will be equal to VR Vs by Z dash into cos theta Z minus delta minus A VR square by Z dash cos theta Z minus theta A. That is what we are seeing is this is the term which is getting subtracted from the earlier term that we had for a lossless line. That is, for a lossy line, the real power is transfer is going to be less, and the maximum power that we can get for a lossy transmission line will be when theta Z is equal to delta. Thank you, and in the next class we will take up some problems on transmission lines.